Hello, everyone. I'm very happy to be speaking at this event today. I helped Sydney organise the European and African versions of this event, so it's been very nice to relax, enjoy watching, and get to speak and not race around for the day. But yeah, my name's Angus Addlesee. I'm a PhD researcher at Heriot-Watt University in Edinburgh, Scotland. I'm industry funded by Wellscope in the Data Lab, and yeah, my PhD is in conversational AI, so pretty useful for this for this event. I'm going to talk today about voice accessibility, adapting conversational AI for specific user groups. Hello, and yeah, I can see the chat and Q&A. I'll hopefully get time at the end to sort of answer some questions live, but if not, I'll definitely sit in the chat and be able to send links and stuff. The main reason why this is the title of my talk is my core PhD is on sort of adapting voice assistants for people with cognitive impairments such as dementia, but I'm also working with many MSc students to build voice assistant for blind and partially sighted users. So, sometimes people pause longer than expected, and even though I started this sentence with some self-corrections like restarts and repetition, you can all understand exactly what I'm saying as I say each and every word. And this sort of on-the-fly listening to each word I say and understanding that as I say each word is very important for something later on. So keep note of that. But these phenomena such as ums and ahs and its and ands and all these sort of speech phenomena are littered throughout our everyday conversation. We all do it and we use it to guide our conversation. So, for example, if I was explaining something about my research to my brother and he went, huh? And that huh would let me know that he maybe doesn't understand something I just said and I should expand on that point. And that would be, mid-utterance. I wouldn't wait for the end of my turn. And these phenomena change as cognition declines. So as people with dementia, their dementia progresses, these phenomena become more common and more pronounced. So pauses, for example, become more common as maybe they forget the word they're looking for, but they're much longer as well. And these sort of pauses are often filled with ums, maybe. And this is very important. So, yeah, we use them every day. They're in everyday conversation, but they're more common and more pronounced in sort of speech elicited from people with cognitive impairments. And we don't just use words. So if I said the thing on the wooden thing, I hope that none of you are going to randomly guess what it is. But this next slide, if I say the thing on the wooden thing, you all know that I'm talking about that laptop. And it's because we don't just chat using words. We use visual cues, we use brow furrows, etc. And I usually pick on the audience here, but unfortunately I can't see any of you. But if you're looking at the screen, looking at me, then I'm sort of assuming you're engaged. If you're looking at your phone, you're probably not. If you're smiling, if you're laughing, furrowing your brow, then I can gauge that you're sort of enjoying or confused, etc. And we all use these. So again, if I use that example of me talking to my brother, he didn't need to say ha. He could just scrunch up his face. And I would expand on that point that I made to explain it because I could tell that that point confused him. So yeah, we sort of change what we're saying as we say it based on both our words, but also visual elements. And current voice assistants don't really take this visual information into account, mostly because they don't have the cameras, which is fair enough. But even these ums and ahs, they often sort of ignore these completely. And I'll talk about that in a little bit in a moment. But they're also trained on very clean data. They're trained on sort of utterances that don't contain these information because they're not trained on sort of everyday natural conversations between two humans. They're trained on maybe people given sentences to read aloud. So, oh, the spoon is on its side. And people get these sentences, they say them very cleanly, and then you get a huge data set upon which you can train your models. and they don't contain these phenomena that are in our everyday language. And that's fine for us, but that's for the majority of people, and that's because we adapt to conversational agents. So what do I mean by that? So I wouldn't say, oh, Google, can you chuck on a timer for a couple minutes? My hands are wet. I would never say that. I would maybe say that to my mum or something, but I would never say that to a conversational agent. I would say, Google, set a timer for 2 minutes. And I wouldn't say that to a human. It's very robotic. That's because we adapt. We know how to efficiently interact with conversational agents, in particular with voice. And that exacerbates this problem. We clean our speech, these systems hear more clean speech, and they are not as good at sort of conversational, phenomena-littered utterances. So what about these people, these groups, who use these these phenomena in their conversation more often? They're more pronounced, maybe older adults who are not used to these systems and don't know to adapt how they talk. How do these people interact? Does it cause confusion with the system? Is it frustrating? And that's a part of my PhD. Spoiler alert, it does. And I'd argue that these groups are people that can make the most use of these voice assistants as well. It's all well and good. I can set a timer while I'm baking without washing my hands. But being able to set thermostat upstairs when you have an arthritic knee is very useful. It saves a lot of actual pain. So yeah, that's sort of the motivation for my PhD. Now, my first paper that I published at the start of 2019, it was a small review paper published at Dialogue for Good. And we looked at the challenges in spoken dialogue, and we looked at why they're critical for those living with dementia. And there were two main things, and that was this turn-taking, this sort of being able to process things word by word, and I'm going to talk about that. I'm going to call that incremental from now on. If I say the word incremental, I'm meaning processing things each and every word, not by a whole turn, like we would say, set a timer for 2 minutes. I'm talking about doing that by word, not by the whole utterance, which most systems do currently. And the other problem is there just isn't the data. There isn't a data set of people spontaneously chatting who have dementia. So how do we know which phenomena are particularly common in this speech? We know sort of where we know some of the things from are from like interviews, say long form interviews, but not spontaneous conversation. So does that change? We don't know. The data doesn't exist. So those are the two main conversations. And here I have a couple of examples that sort of show how this turn-taking isn't natural. If you were talking to a system and you said, can I book a flight to Paris? It says, okay. The light comes on saying it's processing, and you say, no, Berlin. Well, it wasn't your turn. It ignores you, and it says there are flights to Paris tomorrow at 9 a.m., 1 p.m., and 8 p.m. You say, no, Berlin. And it will say, sorry, I don't understand. Because you didn't say, can I book flights to Berlin? You'd have to know to wait your turn and correct your whole utterance. And this is sort of the turn-taking that I'm talking about, which is not natural. If you were at a travel agent and you were talking to a human being there, that would be a very strange interaction. So I looked at speech recognition systems. They take in these utterances, they take in the audio, and they output text, but they do it for full sentences. So I looked at current systems that do it word by word. And there are three major players that do this currently, and that's Microsoft, IBM, and Google. And this WER is the word error rate. So that's what percentage of the words did these systems get wrong? If you look at the bottom row first, that's the non-incremental equivalent systems. So 5.1 there is Microsoft's word error rate when they take in the whole sentence. Then the 30 plus percentage points, that's the incremental word error rates when they're doing each word individually. And you can see that they're getting a third of the words wrong, which is quite bad. The sort of 5% there is nearing human level error rates. 30% is quite bad. So why is there such a big difference here? If I said, I want to cut an edge, and I'm probably not coming across, but that sort of double square bracket is meant to be a confusion there. The system knows that it didn't quite recognize that word, edge, but it doesn't know what it is. If we just were doing this word by word, it would be fair for this system to maybe guess that's the word hedge. I want to cut a hedge. But if the system gets the whole sentence, it can use future words of cheese. And then the system would know I want to cut a wedge of cheese. It's a wedge and not a hedge, because a hedge of cheese makes no sense. So these error rates are much lower because they can use future words to accurately get the word that they're unsure of in the middle of a sentence. Whereas if you're doing it word by word, you don't have access to the words coming up. So that's sort of main reason why they perform much worse. And they're all roughly 30%. So you might think, okay, well, they're all roughly the same. It doesn't matter which one you use. But there's actually a lot of differences, and we ran several experiments showing a lot of charts and different experimental results. We found that Microsoft is the most suitable for our use case, and I'm going to summarize that, but not go into the details. There is the paper, and I don't have time, and it's quite technical, so I'll go through the summary quickly. Microsoft and Google predict their current word very, very quickly. So the current word that's been spoken, they will very, very quickly predict what that word is. They change their mind, so maybe they would output hedge, and then of cheese, it can change its mind to wedge. It's allowed to do that. It's allowed to change what it predicts. Microsoft and Google output their first prediction very quickly, and they stop changing their mind before the word is even finished being said. So if I say the word onomatopoeia, they will have maybe predicted that word and changed their mind on that word before I even finish saying that word. Whereas IBM takes a lot longer to sort of output its prediction and to stop changing its mind, which is not so useful for this use case. Google and IBM also filter these phenomena that I'm talking about, so ums and ehs. If I said the phone is on the table, IBM and Google would output the phone is on the table, which is great for captioning Zoom calls where you don't want lots of sort of extra tokens in the text. It's a bit messy. But for our use case where the could indicate confusion with someone who has a cognitive impairment, it's very, very useful, and we want to keep that. And Microsoft preserves those filled pauses. And finally, IBM was the most robust to speech overlaps. So when people were talking over each other, it was the best at accurately getting both speakers' words correctly. But as I said, there's a lot in there, and there's a paper if you would like to read more. Importantly, none of these systems are yet adequate to reliably handle natural spontaneous conversations in real time. And I'll stress again, this is very important for handling conversations with people that have cognitive impairments who don't know to adapt their speech for these systems. We want to be able to adapt to people, not the other way around. So we released this evaluation framework open source to encourage future systems to try and improve on these scores. And I have one slide on what's next after you have this text word by word, and then I'll move on to a data collection, which is a bit fun. So you get the text of the words word by word. Let's say you wanted to say the sentence, Jane drinks water quickly. Well, you'd get this word Jane coming in, and this circle represents a person named Jane. That's all we know when the word Jane has only been said. When Jane drinks has been said, we know there's some action drinking, and the person Jane is the person doing this action. And we know there must be an object. They must be drinking soup or lemonade or something, but we don't know what that is, which is why there's a blank circle. Jane drinks water. We now know that this blank circle is in fact water. And Jane drinks water quickly. We know there's a modifier term to sort of attach to this action. And there's a paper coming out on this, well, hopefully in a month or two. But yeah, basically we want to represent the meaning of what is said as each word is said, not just getting the text, but the meaning of what is said as the person says each word, which is a huge step towards being able to process and detect maybe confusion in the middle of someone's sentence, and which is very useful, obviously, for people with, for example, dementia. But I'll move on to the problem of there's no data. I had a data collection set for April 2020, which, yeah, possibly the worst timing ever. I wanted people with dementia, who are often older adults, to sit down with random volunteers and have a face-to-face conversation and record that with the video and the audio. So that was postponed for obvious reasons for coronavirus, and I hope that still will take place. But basically, the two people will have a conversation to guide each other through a map, and we should be able to find sort of what both visual and verbal phenomena are most common in a spontaneous conversation. We had to do a lot of ethical work to sort of get this approved. So on the left picture, you can see a device, this wooden box to the left of that board. So there's a device there which can securely capture this data because they might give personal details. We had a consent process. In this picture here, there's the environment we wanted to run this experiment in, which is in Alzheimer's Scotland Centre, and it's looks very cool and classy and modern, and every item in there is designed to be dementia friendly. So the tables, the microwave, the fridge, everything is dementia friendly. It's a very, very cool room, and all of this was thought about and was published in a paper at the LREC Workshop on Ethical Issues, if you are ever wanting to collect a dataset yourself, which I encourage you to do. There's a new ongoing data collection, giving people with dementia Amazon Alexa systems with this device, which is a picture of it being currently soldered and drilled and etc. on my living room table, which has been fun. We're going to record interactions with a voice assistant with people with dementia and be able to detect what the main pain points are, what the causes of frustration, and how do we then use this representation, the circles I showed earlier, to sort of process that and create models to help make this more dynamic and adapt the system to the user rather than us adapting to the system. This latter data collection does miss the visual conversation, but we are doing some work on voice assistants for blind and partially sighted users. I have this sort of picture here just because I don't just publish academic publications, I also publish on Medium, and that's where I have the current article on building voice assistants for blind and partially sighted people. I do hope to have a couple more articles on that coming out soon, and hopefully a paper. But yeah, you can check out there if you would like to read about that more. But essentially, I had 8 MSc students, and I supervised them to build a voice assistant for blind and partially sighted people. And it was fantastic. And this year I had 18 MSc students, which I split into 2 groups, and we worked on 2 different challenges. So I will very quickly talk about these challenges, and I'm hoping to have time to play a very quick video. So the first challenge, interesting point, there's a data set we sort of decided on the challenges from, and that's the VisWiz dataset. It's a huge corpus of images with questions asked about those images from real users who have visual impairments with the correct answers. And you can see sort of such as, does the foundation have any sunscreen? Can you tell me what's in the can? These require questions, the text in the image to answer the question, which is not really something that's covered by current research. So that was one of the challenges. So the first challenge was object related, so counting, color, but also locating items, such as where is my bread knife? It's something that moves in the kitchen. You've never asked where my sofa is. It doesn't really move, but where is my bread knife? It's just to the left of your left hand. And what about my green chopping board? That's just between your 2 hands. So this is very interesting. You're using your hands to sort of navigate to an item. If the hands are not in the image, what the students did, they came up with a clever solution, is using anchor items like a sink or a microwave, which don't really move, to say, oh, it's to the right of the sink. And that's to avoid situations where you'd say the spoon is to the left of the fork and the fork is to the right of the spoon, which is completely useless if you don't know where either of those are. So this was a really, really cool project, and hopefully I'll get time to watch a video on that. And the other group were working on this textual information, so answering questions from packaging, such as maybe spices. What spice is this? Paprika, it could be cardamom, you have no idea. Same with reading how long to cook a ready meal for, or what time you've set your microwave to, or Is this out of date? Does this contain nuts, which I'm allergic to? All of these things are very, very important. And there aren't systems that currently try to sort of tackle this. There are human-in-the-loop systems where you either pay or get contacted with a volunteer who you can send a picture to, and that person would then answer your question. But you get problems such as, how many of this sort of pill do I need to take? Which, if you have an automatic system, if it gets it wrong, it's quite detrimental. But you're having to send pictures of your medication to a random volunteer, and it's maybe not as private. You get into these ethical concerns again. So we've just been working on those two challenges. They've just finished, and I think I have time for a video. I'm going to do it, but thank you very much. I don't think I have time for questions. The video is very, very fast. I'm going to do it now.
Go. Where is the oven?
There is 11 minutes left of the sink here.
So that was, a very, very quick demo. There's a longer video and a video of the other group as well, which I'm going to put on Medium and hopefully in a paper maybe. But yeah, it was just showing that the system is working, and yeah, it's been great fun working with students. So yeah, I think hopefully if you're wanting to collect data or look at sort of phenomena in speech and everyday conversation, then yeah, definitely look out for articles and stuff on that, and feel free to ask any questions. I will answer them in the chat. So as I'm over time, sorry. Thank you very much.